right, welcome back to Physics 325. We're on week 10 now all of a sudden, and this week we're talking about imaging and imaging instrumentation. So we've got two videos, and then we're going to do some example calculations. The first video, today, we're going to talk about what an image actually is and what it takes to form one. We'll go over a few simple image forming devices like poking a hole in something, that's called a pinhole camera. That can form an image. A lens can as well. And we'll develop a kind of very general and powerful framework for dealing with more complicated imaging systems based on 2x2 matrices. It turns out instead of doing a bunch of repetitive calculations, we can grind together a bunch of matrices that will collapse into just 4 numbers that will specify a complex optical system as long as we're in the paraxial approximation. So that matrix optics technique is a very powerful thing we're going to understand today. But just to start off, we have to understand what an image actually is. And we have to think about this. You're seeing me. The camera is seeing me. You're looking around your room. You're forming images of things on your retina. So what is an image? And very broadly speaking, an image is a mapping of a collection of points to another collection of points. Okay? So more generally, we'll talk about a point which gets mapped to a region, right? A perfect image would be a point that gets mapped to a point. But we know from what we found out earlier with diffraction that that's kind of impossible. If we have a point emitter that we can't resolve, and it's getting image, it's going through a circular aperture, such as your eye or a lens, we'll find that that gets collapsed to a blurry region, a diffraction region, that area disk that we saw before. So we can't really map points to points. But a good imaging system is called diffraction limited, and that's going to map points to the smallest spot that we're allowed to. By the laws of optics that give us diffraction. So although that goal is impossible, we'll pursue it nonetheless and talk about what makes a good point-to-point imaging system. So look around your room, look at something, a light bulb or a poster on your wall or whatever you're looking at. It looks like there's an extended image, but really you can treat that as a collection of points, right? And each point on that image, or whatever it is you're looking at, is getting mapped to a region on your retina. Okay, so we have the stuff that we're looking at, we're going to call that object space. We're going to have some abstract imaging system, which could be a variety of things. And on the other side of it, we have what's called image space. And that's the space of the things that the object gets mapped to. Okay, so let's start understanding how to make an image by the simplest possible imaging system, I think, a pinhole camera. A camera just does this mapping. It performs this mapping for you by geometric constraint. So here we have an image of a pinhole camera. We're going to image a tree, it looks like, and we have a box with a small hole chopped out of it, okay, or a little pinhole. So owing to that pinhole, a point on that tree will not be able to map to that whole back plane, okay? So I might have a box, and I'll poke a hole in it, and I'll be looking out this way, and I'll look the other way. We have the light coming in here, and a given point on that tree over there cannot reach that whole surface there because of geometry. So we're going to poke a pinhole with diameter D, and it's going to map to a region of diameter B on the back plane. All right, so let's understand how this works, right? Let's say we have our pinhole here. Let's say the object is a distance L away. So here's a point on the tree, for example, and it's a distance L away. I'll make it blue because I don't think green is good with the green screen, as I've learned in the past. And we want to ask how geometrically constrained our image is based on just putting a pinhole in something. So let's draw another line here and look at the range of possible values we can get to just by virtue of punching a hole in a box. So the situation looks something like this. Rays that are coming at different angles will not be able to get through the pinhole. So we have what we're going to call a spot size B. We have a diameter here, D. And this forms a range of angles we'll call theta, okay? We have a range of angles theta. So just from geometry here, we see that D over L is equal to sine theta, is approximately equal to theta. Also B over L plus this distance, which we'll call F, okay? So B over L plus F is also equal to the same angle, theta. So we can therefore just take the ratio of the two and find that B over A is equal to L plus F over L. Or our spot size, B, the range of angles that a point maps to, is equal to the pinhole size times 1 plus F over L. Okay? So that's what we have here. And note that we've kind of greatly exaggerated things. Typically, objects will be, say, 10 meters away. The box will be like 0.2 meters. And this pinhole will be like 0.0001 meters, right? So this is kind of not to scale, just so you could actually see the angles here. So often it's the case that F is much less than L, in which case we have B is approximately equal to A. All right, so given these constraints here, we have the spot size, the range of points that get mapped to from a given point on the object. That's equal roughly to the pinhole size. More correctly, it's the pinhole size times this correction factor, 1 plus F over L. But often F is much less than L here. L might be a meter, it might be 10 kilometers, or it might be the distance to the sun. If you're looking at a solar eclipse, for example, it's one of these things. So often that's the case. Okay, so that's one thing. We have the spot size, the range of angles, is approximately equal to the pinhole size. What about the resolution of such a camera? How small of objects can we resolve? For example, what about the top versus the bottom of that tree? Is that resolvable? We get the idea that it's going to be somewhat blurry because each point on that tree gets mapped to a point. So two very nearby points. Let's just draw a cartoon of that. If I have a square here, that square will get mapped to another region here. So they'll both be kind of smeared together. So what are the conditions that must hold for me to have a resolved image? Well, let's look at a different object. Let's look at an object here and ask whether or not it's resolvable. All right, so we have these two values here. This is what it would kind of look like. These 2 points would look like on the back plane there. And we have the fact that they're just resolvable here because their spots are separated. This is very much like the Rayleigh criterion for lenses that we studied earlier. Now, what is the angle between them? Well, these two objects have an angle between them, phi. The first thing we're going to do in all these problems is apply the small angle approximation. And notice here that tan phi is approximately equal to phi, and tan phi is b over f, the spot size b over f, which is approximately equal to a over f. And that's going to be our minimal resolution here, okay? So more directly, for any arbitrary distances here, any two arbitrary spots that are separated by delta x, so let's just try to redraw that a bit more generally. So I have a pinhole camera here. I have point 1. It's going to get mapped to a region here. And I have point 2, which is going to get mapped to some other region. And they're going to be separated by delta x. And this is the angle here. Phi is going to be equal to delta x over f, right? Approximately equal to delta x over f. And we're going to have resolved images. We're going to have resolution of our image when delta x is equal to the blur of the pinhole. So that when that's equal to about b, which is about equal to a. So the resolution for a pinhole camera is about equal to its pinhole size divided by f. Okay, so this is the resolution limit here for the pinhole camera. So let's look at what these, have a look at these. Effectively, okay, so this is the resolution limit for the pinhole camera. And we get this expression here. Okay, so this is what some of these pinhole cameras look like. You can make very artsy photographs with them. This is just a box with a hole cut out of it with some film in the back. All right. You can also use these to image distant bright objects like the sun. So here's an example of an eclipse viewer, which is just a pinhole camera. On the left there, you're going to see someone that's taken a picture of an eclipse by poking a hole in a piece of cardboard. And someone's actually made a makeshift one. If you squint your eyes just right, you can see that they've made a makeshift pinhole camera by constraining the sun's image geometrically with their hand. So if you look very closely there, there's also a picture of the eclipse. And we can make one of these ourselves. Okay, so that is the simplest imaging system, the pinhole camera. Let's move on now to the second simplest imaging system, the lens. And we've already seen how this works in previous weeks. So we noticed that a lens already is something that maps points to points, okay? So notice now that we have to be careful where we look. We have to look at a certain distance behind the lens. Our definition of an image is a mapping of points to points. And if we have a point that's a distance DO, object distance away, and we look DI behind the lens, this quadratic phase due to the lens, and we're going to neglect the lens's thickness for now, leads to a new spherical wave that it converges to. So really, we have a new point, a point source that the field is converging to. And this is exactly what we had for an image. Okay, so a lens already does this. And remember when we studied this, we derived this effect of what we call the focal length, the thin lens equation. Okay, so this is the thin lens equation. And this whole slide here is from a previous lecture. So just to remind you, just to recap, that a lens is mapping points to points as well. Okay, so we didn't really go into detail about how to use this though. So let's go into a bit of detail now. Let's just look at how you'd use this in a classical way before we derive our more powerful method. So we'll take a single lens and it has a focal length of 100 millimeters, 10 centimeters. We're going to place an object somewhere and look where the image is. Okay, just to get a feel for this. Okay, so first of all, let's put a object 20 centimeters away from our focus. Okay, so we have our lens here, and we have a focal length here, and we're going to put it twice as far away. Okay, there's our object. And we have to look at something. Let's just see what the thin lens equation says. The thin lens equation is 1 over f is equal to 1 over object plus 1 over image distance. So our image distance is equal to 1 over the focal length, 1 over 10, minus the object, 1 over 20. And I can write 1 over 10 is 2 over 20. Why not? Because then I get 1 over 20 here. So that my image distance is 20 centimeters. Okay, so if that's 20, it's going to appear here. This is where the image is. Let's think a bit about what that image has to look like. Right? Remember that if I had a collimated beam coming into a lens, it would converge to a point at the focus. Okay, so let's take our collimated beam. And we know that it's going to converge to a point of the focus like this. So interestingly, a point from this person's nose, say, gets mapped down here. Okay, we also know that a beam, which is diverging from the focus here, this is from our previous lecture, will come out collimated. Okay, so that will look like this. So a beam which happens to go through here is like the same as a beam that is emerging from this point, and that's going to come out collimated this way. And similarly, for all the points, we'll find, and this was actually in one of the student presentations, we can solve this with the principle of least action as well, all the points here from a given point on the object plane will get mapped here. So this is where the person's nose is. And kind of, we can see where that's his nose, where are his toes. His toes are going to go straight through the center of the lens, so it'll be undeflected. And we can see that you're going to get an upside down picture just from geometry. And that's where the object is going to go. This is called a real image. It's called a real image because I can put a piece of paper up. Let's see if I can grab a lens here. I'm not sure if this is going to work exactly, but I'm going to try to form an image of something with my lens. I'm forming an image of the backlights here. And I don't know if this is going to work at all, but let's try to form an image of the great outdoors. You can kind of see that maybe. If you can hear this, yes, because if not, I will have edited it out. But if you can look right here by my finger here, we can form an image. So I can form a real image, meaning an image which is, if you can kind of see that, which is cast onto a piece of paper. And that's what an image is. All those points from outside are getting mapped to a given point. In this case, this is also a 100 millimeter lens that I just used, a given distance away given by this thin lens equation. Okay? So how about other points? All right, let's look at that. Let's look at if we place our object 5 centimeters away. So now we have our lens, here's our focus again. we'll put this stick figure here. And let's just do the math first. So we have 1 over the image distance again is equal to 1 over the focus, 1 over 10 minus 1 over 5, which we can lazily write as 2 over 10, same thing, and I get minus 1 over 10, so that the image distance is negative 10. That's odd. So what does that mean? If it's negative 10, it's, instead of being 10 this way, it's negative 10 this way. It's behind the emitter. Okay, we need to interpret this. So it says it's going to be right here. So we can think about this. If we had an object, what maybe just do is knee, because the lens I drew isn't big enough, that came away from a point, or sorry, away from the focus, that's going to come out collimated, right? And this is just what we had from before. Now, rays which come in collimated, right, are going to come through the focus, which is equal distance here. So interestingly, we see that the rays are diverging, but that's kind of interesting, because imagine if we had a real object behind here, and there's no lens there, that would also be emitting diverging rays. So if we just kind of clumsily do this and trace it back to where it would have been, his knee is now here, and we have the rays that would result if there was a real object behind the lens. This is called a virtual image. We have an image like this. It's called a virtual image. Why a virtual image? Remember, we just saw we can cast an image onto a piece of paper with a lens. All those rays are converging. We cannot cast this image onto a piece of paper. There's no point which it all accumulates. However, if we take another optical system, our eyes, for example, and we look here, it looks identical to as if there was in this case, a giant stick figure behind the actual object here. So we have a negative image space, which means it's behind here. It means the rays are as if there was a real object at that distance behind the lens. Okay. And finally, let's just plug in 10 centimeters here, just to see what we get. So here's the focus. Here's our object. And we have 1 over the image distance is equal to 1 over focus minus 1 over the object distance is 0. So image distance is infinity, all right? What does that mean for an image distance to be infinity? Let's look at the rays coming out here, the rays from his toe, I guess. They never converge. They don't diverge, nor do they converge. So they kind of, we can see it if we're, depending on where we stand in the 5th postulate of Euclidean geometry, these parallel lines are going to meet at infinity or not. But basically what this is saying is that we have rays which are neither diverging nor converging. So the image is formed at infinity, one way of saying it. It just means that we have collimated light now coming out. So if we put an object right at the focus of a lens, the rays are going to emerge parallel. So we can, in principle, here's an interesting thing. We alluded to this. We can, in principle, make a real image of this giant red stick figure here by putting another lens here, all right? And then we could say its focal length is there, and we could do all the exact same ray methods. These are called the principal rays, by the way, but we won't go into it in this course, this ray analysis, because we're going to develop a more powerful analysis and talk about more complicated optical systems. Because we could, of course, do this piece by piece. We could say we had a couple lenses here, we would see where the image of this lens was formed, and then we would use that lens to image that image, and so on and so forth. But what happens when we get to something like this? That would be a real nightmare to do all that math. So let's think about how we would analyze this. Well, we were kind of drawing these lines before. Let's actually do that now. So let's look at this system one step at a time. So we'll shine in a beam at some angle. It'll hit the first lens and refract. We know how to calculate that from Snell's law. It'll hit the second lens. It'll propagate for a bit, hit another lens, and continue propagating again and again and again. And we can calculate what happens to each ray this way. We could do it using Snell's law if we wanted, but there's a very general way of treating this much more simply, and it's based on this fact, that a fixed location along here, we completely uniquely specify a given ray as a height and an angle. That's all we need. So we can completely specify it with a height and an angle, 2 numbers. Let's throw those into a matrix. We'll call that the ray vector. So it has a height and an angle. That's all we need, all right? And there's 2 things that are going to happen now. As we propagate through this optical system, there's 2 things that are going to, must have violated a law of physics, they're after me. So what happens to this ray vector as it starts off and it propagates through this optical system? Turns out there's only 2 things that can happen, right? It can propagate, so the height's going to change based on what the angle is. The angle's going to stay the same. Light travels in straight lines. Or it can hit a surface, and then it's going to refract right at that surface. The height does not change, but the angle changes, right? So all we have to do is figure out a general way of treating what happens at a surface given the angle and what happens as it propagates. Let's tackle the hardest one first, and then propagation will be easy. We'll tackle refraction at a spherical surface, all right? So let's set up the problem. Okay, it looks daunting at first. It looks very daunting at first because we have all these angles, we have to apply Snell's law, but we're going to be very close to the optical axis. We're going to deal with small angles. We're going to be able to do the paraxial approximation. So remember Snell's law, n1 sine theta equals n2 sine theta 2. Forget it. In the paraxial approximation, we have paraxial Snell. n1 theta is equal to n2 theta. What is theta here? Let's look at what is theta from this diagram. Okay, what theta is, Snell's law says n1 theta 1 is equal to n2 theta 2, because sine theta is approximately equal to theta. But here's theta is, theta is the angle with respect to the normal of the surface. Okay, so let's think about this. We have an angle here. We have an angle that the ray is coming in at. It's coming in at some height and some angle. Okay, so let's draw this out very carefully. Here's my normal. I have a part of my sphere here. And here's the center of the sphere. And I have some normal vector here. Okay, so I can draw this with respect to the normal. So we're going to call this angle beta here. That's the angle that determines where the distance from the center to where our ray actually hits. Okay, and from similar triangles, this is equal to beta and this is equal to beta. Okay, so note that's where the beta here should be moved up. Okay, so we also have an input ray that's coming in at some angle alpha 1 or alpha 1, and it's going to come off at some other angle alpha 2. Okay. Now, what do we have? We have to be very careful about what angle Snell's law is actually talking about. This is the tricky part here. But we can see it's the angle of the ray with respect to the normal of the surface. So we have theta 1 is equal to alpha 1 plus beta. Okay. Similarly here, theta 2, that's this angle here, is equal to alpha 2 plus the same beta. And we can use a bit of geometry here. If this is a height h above the axis, then we have beta is approximately equal to sine beta, which is just h over r. Okay, throw that all together, and this is what we get. Okay, so let's think about how that actually acts on our ray. So plugging this into Snell's law, we have n1 alpha 1 plus n1 h over r is equal to n2 alpha 2 plus n2 h over r. So let's solve for our new angle here. So n2 alpha 2 is equal to n1 alpha 1 minus n2 minus n1 over r times h. And here's the key here. Alpha 2 depends on alpha 1 and h. It's some number times alpha 1 plus some number times h. That is a matrix multiplication. What matrix gives us that? Well, we better actually write it purely in terms of alpha 1 and alpha 2. So we're going to get n2 here. And we can see that this corresponds to a matrix multiplication that looks like this. Note, by the way, that this n2 minus n1 over r, that's 1 over what the focal length was for our lens here. So this is the matrix corresponding to a single refraction. Seems like a lot of work, but it will pay off. Believe me. Bear with me 1 second because we have an easier one to solve now. How do we solve translation? Translation is just at a constant angle. Basically, we're going in a straight line, and we have some angle alpha. So the height, if we've gone a distance d, is given by d times tan alpha, approximately equal to d alpha. All right, so it's independent of the height and only depends on alpha. We can just write that as a very simple matrix like this. Okay, so we have our two matrices. We have translation and we have refraction at a surface. We've done all the work. Let's get the payoff now. First of all, the first thing we can do is find out what a thick lens actually does versus a thin lens. Okay, so remember we neglected the thickness of the lens? There's no need to do that now. We have the arsenal that we need. So we can easily include it. And for simplicity, let's just, this is almost always the case. Let's assume that our lens is immersed in air and it has an index n. Okay, so what happens to our ray matrix? Well, the first thing we do is we hit the first surface. So that is a refractive surface like this. All right, then we translate a distance d. And finally, we hit the last surface. This is just a matrix. It's just 4 numbers. We can grind out, it's kind of messy, we can grind out what those numbers actually are, but every time we go through a thick lens, this is what happens to both the height and the angle going through this. Now you can do this by hand, or often you'll just plug it into Python or something like that, and you'll get a number of, 12, -3, 3, 14, or something like that. So what can we do with that? Well, let's send in a collimated beam. And it's going to do some bending. Okay, so it's going to come out at a new height, h2, and an angle, alpha 2, and it's just going to be given by these numbers here. Let's just call them A, B, C, D. So h2 alpha 2 is equal to A, B, C, D times whatever came in, h1, and let's set alpha 1 to be 0 here, okay? So what are our new values here? So I'm sending in collimated light, and it's going to come to a focus at some point after. Let's just do this matrix multiplication. That gives me h2 is equal to A times h1, and alpha 2 is equal to C times h1. Okay, that's pretty good. That's actually quite nice, because why? Imagine we come some distance away. I don't know, let's call it F, for reasons that will become clear very soon. We have the angle, alpha 2, is equal to, in the small angle approximation, h2 over f, okay? So we have, plugging these numbers in here, C times h1 is equal to A times h1 over f, right? That's what h2 is. These h1s cancel, it's independent of h1, and we get a new focal length, which is merely A over C here. And we can actually just plug that in there. So given A and C, we can get the new focal length. All right, so that's what the new focal length of our thick lens is. All right, so one thing that's nice about this is it reduces to the thin lens. So let's look at what we have when we plug in D is equal to 0 here. When D is equal to 0, we have neglected the thickness of the lens. Okay, so we get we get this matrix here. All right, so this focal length, technically it's called the back focal length because it's the distance from the back of the thick lens to the focus. we can get directly from this matrix here that we get from multiplying everything out with d is equal to 0. And we see we have a new focal length here, a back focal length, which is the same as a focal length if the thickness is 0, given by 1 over that focal length is 1 over f1 plus 1 over f2. Lenses or surfaces, it turns out, add like resistors. They add in the inverse. That's kind of a neat result here. Okay. We can also plug in the form that we had for the individual f's, right? And this is what we call the lens maker's equation that we arrive at. So we have 1 over f is equal to n minus 1 times 1 over the first radius of curvature minus 1 over the second radius of curvature. All right, so we get that directly from this matrix. And this is the matrix of a thin lens. 1, 0, 1 over, negative 1 over f, 1. So now we're getting closer to what we had before. We had multiple lenses. Let's see what that would look like, okay? So imagine we had this crazy lens system here, and we want to know what happens to each individual ray. Well, that's just a long string of matrix multiplications. Transmission, lens, transmission, thin lens, translation, transmission, thin lens, all the way out, and then the final transmission. Okay, so we could grind that out if we wanted. In this case, it would look like this. Now, I wouldn't recommend that you ever do this. I would plug it into a computer and get it to grind out the numbers for you, because it's just going to be 4 numbers, A, B, C, D. So this whole mess here is just some set of actual numbers, right? And we plug in a given ray then. Anytime we want to know what happens to a ray that goes through this thick multi-lens system, it's just a simple 2 by 2 matrix times a vector, right? So that's a total of what? 4 multiplications, a couple additions, and we're done. Super fast way of treating this, but and also very interestingly, it treats this whole system as a black box. We don't think about each individual lens here. We just have 4 numbers which quantify the optical system. And this is the real power of matrix methods in optics, okay? And now we can really see how, when we had that mess of lenses that we showed earlier, how we'd actually calculate that. So let's summarize. This has been quite a lot. Matrix optics. So first of all, we talked about what an image actually was. An image is a mapping of a set of points to a set of points, and maps to an object in object space to an image in image space. Okay. The simplest way to do that is to poke a hole in something. We can constrain things geometrically and make a pinhole camera. We can also do this with a lens. We saw that earlier, that a lens just does that. It takes a spherical wave and it maps it to another spherical wave. And that already gave us the thin lens equation. We can actually look at this in terms of matrices. Only 2 things can happen to a ray. A ray is specified by an angle and a height. The angle can change and the height can change. That happens with a surface with a radius of curvature and a translation, respectively. So given that, we can write everything as a 2 by 2 matrix acting on these two-dimensional ray vectors. The thin lens had a very simple matrix that was multiplied by h and alpha. We also could attack thick lenses and any kind of arbitrary set of things with both the translation matrix and the refraction matrix. So we'll let you have some fun playing with these in the assignments, and that's it for today. So we'll see you next video.